Hi, my name is Rasmus Birn, and what I want to talk to you about today are quality control procedures and metrics, specifically for resting state fMRI. I have no disclosures. The topics that I plan to cover are first, what are the main issues to look out for in resting state fMRI data? And then I will be covering a number of quality control or QC measures, both qualitative and quantitative. And then I will try to address two questions: what motion censoring threshold to use, and whether or not we should be using bandpass filtering. The main issues could essentially be grouped into four categories: errors or inconsistencies in the imaging parameters, artifacts or other abnormalities, issues related to alignment of the images to template space, and head motion. Now, these first two occur rather infrequently, and in my experience, the most common problems have to do with alignment to template space or head motion. So what quality control metrics can we use to address these? Well, for errors or inconsistencies in the imaging parameters, we could look at potential flips in the left-right direction or smoothness of the data, the full width half maximum. In order to identify abnormalities or artifacts, we can look at the temporal signal-to-noise ratio or the functional connectivity strength, which is the average functional connectivity of a voxel to all other voxels in the brain or in the image. For alignment to template space, we can visualize these qualitatively, but we can also calculate some measures of the overlap between the anatomical and the template, or between the EPI and the anatomical, like the dice coefficient. And finally, to assess motion, we can look at the mean volume to volume motion, for example, calculated as the Euclidean norm or E norm. We can look at the maximum of that value, and we could look at the number of good volumes that are remaining after motion censoring. And finally, I'll introduce a new measure that we can use to guide some of these choices, and that is the similarity of the individual's functional connectivity matrix to the group functional connectivity matrix. I'll be spending most of my time talking about these last two issues, alignment to template space and the head motion, because I think the first two are rather pretty straightforward. One way we can check the alignment of the images to template space is to take one brain image from each subject and then concatenate them together and play them as a movie. So at the top, you can see I've taken one T1 weighted or structural image from each subject, concatenated them together. And at the bottom, I've taken a single EPI image warped into template space and then concatenated them together. And if we play those as a movie, you can see pretty good alignment between the T1 weighted images. Now we can either play them as a movie, or we can take the scroll bar and just move this backwards and forwards and check the alignment that way. And similarly for the EPIs, we can scroll around and we can check the alignment of the images to one another. And we can identify some potential outliers, such as, for example, this one showing a little bit larger. And these are largely due to challenges or errors in alignment between the echoplanar image and the structural image. You also notice here a little bit of an odd one. This looks like it's upside down. And this was actually an error in how the image was converted into the Nifty file. So there was an error in that header information. So we can flag these potential problems. Another way to do it is using the output from AFNI proc. The display is a little bit different, but the concept of this is the same. What you see here is the underlay is the echoplanar image warped into template space, and then in overlay in red, you see the traces of the sulci from the structural image. We can check what the alignment is, and you can identify, see if there's any misalignments between the T1 weighted image and the EPIs. So can we quantify this alignment? Well, one way we can do that is using the dice coefficient, which is basically a measure of the overlap between two different masks. In this case, a mask of the echoplanar image and the mask of the anatomical or T1 weighted structural image. Now, in my experience, this measure doesn't always work very well. At the bottom here, I'm showing you the histogram of the dice coefficients. And in this particular case, I'm showing a particular subject that has a fairly low dice coefficient relative to the rest of the distribution. And you can see, indeed, there's some misalignment with the echoplanar image sort of protruding out in the superior direction from the T1 weighted structural image. So correctly identifying this as potential misalignment. Now, this subject actually has a dice coefficient very close to the average of the group, but you can see a pretty substantial misalignment between the EPI and the T1 weighted image in this participant. Now, in this subject, we see a fairly reasonable alignment of the brain across most of the cortex, but we have a very low dice coefficient between the EPI and the T1 because of the prominent signal dropout in the orbital frontal cortex. And this signal dropout is not something that a registration algorithm could really fix. Now, moving on to the issue of head motion. One common way to reduce the effects of head motion is to censor time points where the volume-to-volume motion exceeds some threshold. What I'm showing you up here in the left are the 3 translation and 3 rotation parameters estimated from a subject whose head was moving slightly in the MRI scanner. And what's particularly important for the impact on the fMRI signal are the volume-to-volume movements. And so we can calculate the volume-to-volume translations and rotations, and then either calculate the sum of the absolute values, which is called the frame-wise displacement, or we can calculate the square root of the sum of the squares, the Euclidean norm of these, and that's what I'm plotting at the bottom here. And then in green, I'm indicating those time points where the Euclidean norm or E norm exceeds some sort of threshold, in this case, 0.4 millimeters. Now, following this, to quantify this motion, we can then calculate the number of good frames that we have remaining, the number of good volumes we have remaining after the censoring. We can also look at the mean Euclidean norm or the maximum amount of motion, this maximum Euclidean norm. We can also look at the impact of this motion on the functional connectivity. Now, in order to get a more holistic measure of the functional connectivity across the whole brain, we can parcellate the brain into a discrete set of regions of interest. In this case, I'm showing you the 333 regions from the Gordon parcellation. And we can average the signal over these regions of interest and calculate all possible querized correlations to form this connectivity matrix. And I've organized this connectivity matrix according to the different functional networks that you see here. Now, one common measure used to assess the impact of motion within the group is to calculate the correlation with motion, what's called the QCFC metrics. That is, you take the quality control metric, in this case, the mean Euclidean norm for each subject, and you take the functional connectivity matrix for each subject, and then you calculate the correlation of each connection with this quality control metric. What I'm showing you here at the bottom is a histogram of these correlation values. And I've shown this here for 3 different motion censoring thresholds, 0.2 millimeters, 0.4 millimeters, and 1.0 millimeters. And in this particular population, there really isn't a whole lot of difference in these histograms, that is, in the correlation with motion for these different motion censoring thresholds. Another measure we could look at to assess the impact of motion on functional connectivity is to look at the similarity of each subject functional connectivity matrix to the group average functional connectivity. The idea being that if a particular connectivity is corrupted by motion, it would look less similar to the group average. Now, this measure, of course, we have to use it cautiously because ultimately in a lot of studies, we're interested in looking at individual differences in the functional connectivity. However, what we can look at is how that similarity to the group average varies with different amounts of motion. So what I'm showing here on the right is a plot of the similarity. That's the Pearson's correlation coefficient between each individual subject's connectivity matrix and the group average for the different subjects. And on the x-axis, showing the mean Euclidean norm, the mean amount of motion for each participant. And as you can see, as you would expect, as the amount of motion increases, the functional connectivity matrix becomes less similar to the group average. So now what happens when we change the motion censoring threshold? Now, first you might think, well, compared to which group average, right? Should we be comparing it to the group average from the less stringent motion censoring? Well, it turns out it doesn't really matter. The group average connectivity is actually highly similar across the different motion censoring thresholds in this particular sample. So what I'm showing you here are the average functional connectivity matrices from a motion censoring threshold of 0.2 millimeters, 0.4, and 1.0 millimeters. And you can see that they're highly similar. And if you just plot the connectivity values of the different motion censoring thresholds relative to one another, you can see how highly correlated they are. And similarly, the similarity of each subject's functional connectivity matrix to the group is essentially identical regardless of which group you compare it to. In this case, the 0.2 millimeter or the 0.4 millimeter motion censoring thresholds. Okay, so this is the relationship between the similarity and the mean amount of motion that we had at a motion censoring threshold of 0.2 millimeters with bandpass filtering. So what happens if I now relax that motion censoring threshold? Well, what I would expect to happen is that as we relax our motion censoring threshold, we allow more high motion time points into our data, and that should mess up the functional connectivity, particularly for high motion subjects. So we should see a decrease in the similarity, particularly for the high motion subjects. So here's what we actually find. So what I'm showing you here, this is for the motion censoring threshold of 0.4 millimeters and 1.0 millimeters. And if I calculate the difference between, say, the 0.4 and the 0.2 millimeters, I get this difference here, and similarly between 1.0 and 0.4 millimeters. So this was actually a bit surprising to me, because what this is saying is that particularly for the more high motion subjects, if I relax my motion censoring threshold from 0.2 millimeters to 0.4 millimeters, the similarity increases. That is, the functional connectivity matrix looks more similar to the group average, kind of the opposite of what we predicted. So let's take a look at a case example. Here's an example of a connectivity matrix for one subject, subject 104, that had a considerable amount of motion. And what you can see here is the connectivity matrix from a motion censoring threshold of 0.2 millimeters compared to 0.4 and 1.0 millimeters. And at the bottom, I'm showing the group functional connectivity matrix. And you can really appreciate how noisy the functional connectivity matrix is at this very stringent motion censoring threshold of 0.2 millimeters. So what's going on? Well, if we take a look at the motion time series, that's what I'm showing you at the bottom here. And in green is indicated which time points are censored for the different motion censoring thresholds. And what happens is that as we censor more and more time points, the degrees of freedom decreases. So the degrees of freedom we have left for 0.2 millimeter is only 7 degrees of freedom, and then 36 for the 0.4 and 50 for the 1.0. So why are we losing this many degrees of freedom? Well, we started with 152 time points. These were 5-minute long runs. We lose anywhere between 0 and 43 time points due to the motion censoring. Another 21 degrees of freedom from all the nuisance regressors that we added in, that is the average white matters, the CSF, the motion time courses, polynomial fits, and so on. And we lose an additional 81 degrees of freedom because of the bandpass filtering that was done. So let's look at the effect of bandpass filtering. At the left, I'm showing you that same relationship again with 0.2 millimeter with bandpass filtering, how the similarity decreases with increasing amounts of motion. If I turn off the bandpass filtering, the similarity increases, particularly for the high motion subjects. And here at the bottom, I'm showing that difference between no bandpass filtering versus bandpass filtering at 0.2 millimeters. And you can appreciate that the similarity increases without the bandpass filtering. So here's an example, just to illustrate that for one participant. At the left, I'm showing a functional connectivity matrix with bandpass filtering at a motion censoring threshold of 0.4 millimeters. And at the middle, you can see without bandpass filtering at 0.2 millimeter threshold, and on the right, without bandpass filtering at 0.4 millimeter threshold. And you can see how much noisier the functional connectivity estimate is when bandpass filtering is employed. And this is directly related to the degrees of freedom. In this case, on the left, we have only 7 degrees of freedom remaining, whereas in the middle, we have 45, and on the right, we have 94 degrees of freedom remaining. And if we directly plot the similarity versus the degrees of freedom, you can see a roughly linear relationship that plateaus out, where basically at a certain point, when we get below a certain number of degrees of freedom, the similarity just decreases. At the top, I'm showing this for a 0.2 millimeter threshold, and at the bottom, I'm showing this for a 0.4 millimeter threshold, both of these with filtering. So the quality control criteria that I came up with for this particular data set was if we had fewer than 15 degrees of freedom left after motion censoring, nuisance regression, and bandpass filtering, that subject would be excluded from further analysis. I also had a criterion that we wanted at least 4 minutes or 240 seconds of data remaining after motion censoring. The censor threshold that I chose was 0.4 millimeters. Now, the more data is always better. And a typical cutoff that's been used in the literature is having at least 5 minutes of good data. Well, in this particular data set provided by OpenQC, we only had runs that were 5 minutes in duration. And so any kind of motion censoring would cut into that. And so I relaxed that just to be able to keep some participants to keep 4 minutes of good data. I also looked if the maximum frame volume to volume motion exceeded 3 millimeters, that subject was flagged and further examined. It turned out in one case that motion happened right at the end, so those images could just be discarded and the subject could still be used. The concern with large amounts of movement is that it could introduce changes in the Bezier field or movements into different parts of the coil sensitivity, which could be more difficult to correct. However, as I've shown in a recent publication, if that motion occurs rather infrequently, there are ways to account for that. If the data were left-right flipped and the correct orientation could not be determined, that subject would be excluded. We also looked at the temporal signal to noise and the functional connectivity strength. If there was indication of a presence of a coil artifact, we would exclude that participant. We didn't see any in this particular data set. Again, if some of the cortex was outside the field of view, just qualitatively looking at the data set, we would exclude that subject. Again, we didn't exclude any in this particular sample. And we also looked at potential abnormalities in the anatomy qualitatively. And finally, if there are any significant misalignments in the data to template space that can't be fixed with different processing choices, we would choose to disregard that subject or exclude that subject from further analysis. So in conclusion, number one, I would say look at your data, both during the acquisition, ideally, because then you have a chance to actually fix any problems that might occur, and also look at it at multiple points during the pre-processing so that you can find out where things might have gone awry. There are a number of qualitative metrics that I found very useful, like visualizing the anatomy and the EPI and the alignment. And then there's a number of quantitative metrics, potential left-right flips, temporal signal-to-noise ratio, functional connectivity strength, the mean and maximum amounts of motion, number of good volumes remaining, and this similarity to the group mean. But I use this measure mainly to try to guide what other QC criteria to use, such as the motion censoring threshold, and to look at how this similarity, for example, varies with the amount of motion. And finally, in relation to those last 2 points, motion censoring threshold of 0.2 millimeters is common in the field, but it may not be appropriate for the particular data sets. I think it's important to consider the degrees of freedom that one has left and not be overly stringent in censoring so that you don't have enough data to get an accurate estimate. Now, bandpass filtering, for example, keeping only those frequencies below 0.1 hertz, is very common in the field of resting state fMRI. However, it may not always be appropriate. The original motivation for doing the bandpass filtering was to make sure to exclude cardiac and respiration fluctuations and only focus on the lower frequencies that were driving the functional connectivity. However, at the typical TRs that we are now using for functional MRI studies, like the 2 seconds in this OpenQC studies, the physiological noise is aliased to these lower frequencies and therefore not filtered out. In addition, there is increasing evidence that there's functional information at higher frequencies. So I would urge people to revisit the idea of whether or not we want to do bandpass filtering, and in particular, consider the degrees of freedom that are lost. This is also a problem for the newer connectome-style acquisitions that acquire data with very short TRs, like 800 milliseconds, where if you filter the data and only keep the very low frequencies, below 0.1 hertz, you're throwing away a lot of degrees of freedom. So thank you for your attention.